Now let's look at finding the domain of a function given that the function is defined with an equation. When you have an equation and you want to think about what you can use as an input, you want to think about what it's possible to calculate with. What number can you throw into that function and still retain a real number? Because we want our domain and our outputs to all be real numbers. So our domain and range needs to be real. So think about the calculations that would allow you to retain a real number. Well, things you can definitely do is you can always add two real numbers together and get a real number. You can subtract two real numbers and get a real number. You can multiply two real numbers and get a real number. You can square or cube or take to the fourth power, any power, two numbers and still have a real number. There's no problem with all of those operations. But what you cannot do relates to division and then certain roots. Specifically, you can never divide by zero. When you divide by zero, you get a number that is unreal. In fact, it's undefined mathematically. Another way, a more common way to see that is that division can be represented by a fraction, and you never want a zero in the denominator of a fraction because that implies that you're dividing by zero. So a fraction cannot have a zero denominator. Square roots cannot have negative inputs. If you try to square root a negative number, it doesn't make sense if you're working in the real number system. It would only make sense if you allow for imaginary numbers. We're not going to do that with domains and ranges of the functions we work with this term. We want to stick to real numbers. So we're going to also be concerned with square rooting a negative number. It's okay, it turns out, to cube root a negative number. You can cube root a negative number and still get a real number, but you can't take any root that is an even index. So a square root, a fourth root, a sixth root. If you do that with if you square root a negative number, a fourth root a negative number, you will get something imaginary. And we want to stick to the real plane when we talk about domain and range. So let's look at three examples. The first example, f of x equals x squared minus 2x minus 5. If we think about the calculations here, there's a square, which we know is fine. We can always square any real number. There's a multiplication, 2 times x, which is fine for any real number. And then we've got subtraction. And subtraction, again, is perfectly fine. Subtraction or addition is perfectly fine. So there's nothing in this function calculations that would cause any problems. We're not dividing by zero. We're not trying to square root anything. So the domain in this first function, f, would be all real numbers. Now, sometimes people also will say it's the set of x such that x is an element, we use this kind of fancy looking e, of the real numbers. Now, a way to abbreviate the real numbers is with a capital R with a double bar on the R. That's another way in set notation to write this. And a third way would be in interval notation. To show all real numbers in interval notation, we just say negative infinity to infinity, with the parentheses around each. So that would be an interval notation for all real numbers. So three ways you might see that a domain of that type of function written. Now in our second example, g of x equals 2 over x plus 5. We've got a denominator here. And remember, we can't divide by 0, so this denominator cannot be 0. We need to exclude any number for x that would make that 0. So to figure out numbers that would make that 0, the best way, if you don't see it immediately, just as is to actually take the denominator and set it equal to 0 and figure out by solving what would make that 0. To solve this, we would simply subtract the 5 from both sides, and what we see is x equal to negative 5 would yield a 0 denominator. So we exclude this value because it makes the denominator 0. So what we would want to do is we would want to talk about the domain as being all real numbers except negative 5. So we can write that out, or we could say the set of x such that x is not negative 5. This would be using set notation. When we use the set notation where we say the set of all x such that, we're implying that x is a real number. It's all real numbers except what we put in the exception of x not equal to negative 5. And then in interval notation, what we want to do is take all real numbers, which we had as negative infinity to infinity, and break that up where you have this exception. So you start with negative infinity, and you go to that exception of -5 and use a parenthesis. Remember, parenthesis means you exclude the number to break up the set right at -5, and then we use a union symbol to show that we start up on the other side. So this would be the interval notation for showing all real numbers except -5. We break up the real number system at -5. We exclude it with those parentheses. In the third example, h of x equals the square root of x plus 3. We've got a square root, and the square root is something we have to watch out for. We cannot square a negative in there. So that x plus 3, which is entirely inside the square root, cannot be negative. So what we want to do is prevent it from being negative. Well, if we want to prevent it from being negative, then we want it to be positive. So we could say x plus 3 needs to be greater than 0, or there's no reason it couldn't be equal to 0 because the square root of 0 is 0. So we generally take the inside of the square root and say it has to be greater or equal to 0 to avoid it being negative. We can then solve for x by subtracting 3 from both sides, so x must be greater or equal to -3. So what we have here is a restriction on x. X can't be lower than -3, it must be greater or equal to -3. So with the domain of this function, we would say all reals greater or equal to -3. Running out of room there, sorry about that. Or we could say the set of x such that x is greater or equal to -3. That would be set notation. If we wanted to show this in interval notation, we would say that x is at its lowest at -3. Because of the equals, we would include the -3 with a bracket, and we'd go up to infinity because it can be any higher number than that. So there's 3 ways we could write that domain out as well. So again, make sure you watch out for dividing by 0 and negatives inside of square roots when you're thinking about domain. It takes a while to get used to finding the domain from an equation of a function. So here are 3 examples to try out on your own, and then maybe pause the video, and then when you think you've got them, unpause and I'll show you my results. All right, so let's look at these 3 examples. K of x equals 3x minus 5. So what you're doing here with x is you're multiplying by 3, which is no issues at all, and then we're subtracting by 5. Again, multiplication and subtraction isn't going to affect anything about getting a real number. So K would have all real numbers as its domain. We could say -infinity to infinity in interval notation. The function m, here to the right, has a square root in it. So this inside of the square root, remember, can't be negative. So what we would want to do is say, well, the inside, what we also call a radicand, must be greater or equal to 0 because it needs to be either positive or equal to 0. It cannot be negative. This inside can't be negative. So to avoid that, we put this restriction on. Now we solve. To solve, we would move the 12 to the other side. It's positive where it currently exists, so when we move it to the other side, we would subtract. So we get -5x is greater or equal to -12. Next, we would divide out the -5. And because we're dividing by a negative, we're going to end up having to adjust our inequality symbol. There's that rule about dealing with inequalities, that if you divide by a negative, you must switch the symbol. So this is going to be x is less than or equal to -12 over -5. Now we should simplify this. The only thing that technically simplifies is the negatives. Negative divided by a negative is a negative, or positive rather. So this becomes 12/5. You could write that as well as x is less than or equal to 2 2/5 or 2.4, your choice. Generally in mathematics we like the improper fraction a little better unless it's an application. So at this point, if we wanted to say this would be all reals less than or equal to 12/5, or we could say because it's less than or equal to that number, we would go down to negative infinity and then go up to that highest number of 12/5, include it because of the equals. If you wanted to write it in set builder notation, you could say the set of x such that x is less than or equal to 12/5. So there's 3 ways to write that domain out. All right, in our last example, we have p of x equals x plus 2 over 2 times x minus 8. Here we've got a denominator, and remember a denominator cannot be equal to 0. So what we want to do is figure out what will make this denominator 0. Fix that typo. And then, so we set it equal to 0 and solve. 2x equals 8 when we add the 8 to both sides, and then divide out the 2. 8 divided by 2 is 4. X equals 4 makes the denominator 0, and we do not want the denominator 0, so we're going to exclude that value from the domain, exclude 4. So we're going to say all reals except 4 in our domain. Or in interval notation, we say from negative infinity to 4, pop the 4 out, and then union the other side. Or we could say the set of all x values such that x is not equal to 4. So we exclude the 4 by saying what cannot be in the domain. So 3 ways of showing the sets of these domains.